Okay, good morning, good morning. Welcome back. I hope we had a wonderful break. So first thing I want to say is thank you for allowing me the flexibility to go on my trip right before break. I really appreciate that. So we have lots of announcements. You can see a zillion things open up on the bottom of the smartboard here, but we're missing a few people. So we'll wait on the announcements and we'll just kind of check in with each other. So first, in case you didn't check your email over the break, the quiz that was supposed to happen today is now a take-home. It's on your table, so go ahead and grab one. We can talk about that in a few minutes. But what I'm really interested in knowing is how did the YouTube thing go for these two classes that I wasn't here for? What was that? Okay. All right. Well, the two videos got lots of views, so I think that's a good thing. How are we doing on the material from those two classes? Anybody have any questions on either 8.1 or 8.2? So maybe real quick, if there aren't any specific questions, I can take a look at one question that Dawn had asked about. Yes. Yes, test 3 is on May 8th. Welcome. Do you not have a copy of this calendar, Angus?
I'm not sure we have
Hi. Okay, let's see. So. All right, so there was one question that Dawn had asked me about, and Dawn, maybe you can help me remember the equations, but I think it was y equals the cube root of x, is that right? And 4y equals x? Yeah. This was number 21, I think, from the most recent homework. And we're going to take the region that's enclosed by those two curves, and we're going to spin the region around x equals 9. And we want to find the volume of this crazy region. So the first thing we need to do is draw a really good picture for all of these things. And you know, the quiz that I just handed out, so again, it's now a take-home quiz. Make sure you grab one from your table. It's due first thing on Wednesday. It's the same rules as a regular quiz. This is a non-calculator quiz. I trust you to not use your calculator on it. So if you can't use your calculator, it means you really you better be good at drawing some of these basic graphs, because you need to have a nice picture in front of you to pull it apart and set up your integral. So there is on the quiz, there is a time limit of 25 minutes, but that's a very loose time limit in class, so it can be loose for you at home, right? So you can pretty much ignore that, but no calculator, no resources other than you know, your index card if you have one. Okay, so let's draw a good picture of this thing. So the cube root of x looks an awful lot like the square root of x, which is this guy. But what's the difference between the cube root and the square root? So this continues, right? This one is defined for negative x's. So that right there is the cube root of x. And then 4y equals x. Some folks would solve that one for y. You don't need to, but you can. So it's x over 4, which is what kind of a thing? That's a line. So we'll draw the line. And it might not be clear to you, you know, like maybe the line goes like this way, or maybe the line goes this way. It's sometimes hard to know, and depending on which, like, you got to know which one's on top. And so if you don't really know what's happening, what you can do is, for example, you can plug in x values into both of these equations. So you've got the cube root of x, and you've also got x over 4. So for example, I could plug in 0, 1, and 2 and just see, like that would give me some points, and then I can compare which one is on top and which one is down below. What's the cube root of 0? Is 0. And when you plug 0 into 0 over 4, also 0. So they're tied at the origin. Cube root of 1 is 1, and over here 1/4 is 1/4. Okay, so apparently the line is below because 1/4 is less than 1. And when I plug in 2, cube root of 2 is some messy number, I'm not sure. 2/4 is over here. With your calculator, you can check and you'll find that the cube root of 2 is still bigger than a half. Right? And so this gives me a good sense that the line is under. They meet here, the line is under here, but it sure feels like with the line chugging along at this constant growth rate and the curve kind of not leveling off, but it's growing slower and slower, it feels like they're going to meet up at some point. And it seems to me like that space right in there is the region that we're interested in. So really take your time as you're drawing the regions. If you don't have a good picture, you're not going to be able to set up the integral. Okay, so there's the region. You need to find the point of intersection. It happens that the point of intersection is 8, 2, and the other point of intersection here is 0, 0. And so that's the space that's completely enclosed. And then x equals 9, which is the thing that we're spinning around right here, is a vertical line, and it is slightly to the right of this point. This point is at 8, 2, so we're going to draw a vertical line just a little bit to the right. X equals 9. So you're taking that region and spinning it around this line. And a really good question that Dawn had asked, and I'm going to bring here to the class, is, okay, so we see the yellow region is enclosed there. What about this green space? Is it not also enclosed? Should it not also get spun around that line? What do we think? Does the green region count? Okay, so maybe we got some negative stuff because the which curve is on top has changed. Fair enough. Tassiday, you say doesn't count? Yeah, it's not bounded by the right things. It is bounded by the red and the purple and the dotted black line, but the dotted black line is the thing you're spinning around, and that has nothing to do with the boundaries of this region. There are exactly 2 boundaries for this region. It's these 2 functions that were given here, the cube root of x and 4y equals x. Those are the 2 things. So the only region that's enclosed by those 2 things is that yellow space. And the dotted line doesn't count as being part of a boundary. It never counts as being part of a boundary unless it's explicitly given as part of the boundary. And in a lot of the early homework examples, you'll see stuff like, y equals x squared and x equals 2 and y equals 0. That space in there. Why did I stop at the x-axis? Because that's what y equals 0 is. And maybe in the first few homework examples, you're not really even thinking about it. You just say, oh, it always goes to the x-axis or always goes to the y-axis. And then maybe I say spin it around the x-axis. And it happens that that is part of the boundary, but it really has to be listed there twice. If the thing you're spinning around is part of the boundary, it's going to be there twice. And so maybe it's a good idea to check out some of the early homework examples now, really watching for that, because it might have been something you took for granted when you were just getting the hang of this. Okay, so so that's the picture and that's the setup, and then you run through and you write down your integrals based on that. So we're not going to go any further than this. Although I will say one thing: I think the answer in the back of the book for this was wrong, or at least incomplete. Is this the only, that yellow space? Is that the only region that's bounded by the 2 curves? There's another one to the left. If we had continued this red line, and it continues forever, and we continued our cube root function, then we'd have another region right in here. And I read that question a couple of times trying to see, did they exclude that somehow in the directions? And I don't think they did. So the answer in the back of the book only takes care of taking the yellow region and spinning it around. And I think it's correct in what it does. But I think the answer in the book should then have a plus and then some other brand new integral to take the green thing and spin it around. Okay, so let's go ahead and take care of some of these announcements. And again, I appreciate your flexibility with the YouTube thing and letting me go on my trip. So lots of announcements. Okay, first of all, we talked a little bit about the quiz number 4. It's on the table. Make sure you grab one. It is a non-calculator quiz. It is now a take-home quiz. Hand it in first thing on Wednesday. You can put it right in the folders. So project number 5, I assigned a long time ago now. It's due on March 29th, which is this Friday. So project 5 is the one with the 4 candies, the 4 chocolates. Everybody have the 4 chocolates? Yes, Maggie?
My egg thing got smashed in my backpack, so I got more, but I threw it out. But when I went there, I'm like, this is bigger than the one that I had.
I can give you one. You can do the one you have. Just turn yours in.
I figured you.
Yeah, that's fine. Yeah, right after class, just remind me. Okay, so that's the project on chocolates. It's there. The Gamma project, I'm almost done grading them. I just have 2 questions left to grade on everybody's. So I'll hand those back on Wednesday. Next thing. So right now we're at the start, or kind of a couple of classes in now, to all of the applications of the integral. And so over the next few weeks, we're going to talk about some more geometry stuff, volume things today. Next class, we'll do some physics stuff, density and center of mass. We'll talk about work and other physics application. Then we'll do some economic stuff. And then we'll wrap up the applications with some probability stuff. So all kinds of different scenarios where apparently the integral is useful. So that's what's coming. And it's a ways away, but not too early to start thinking about test 2. It's on April 8th. I don't have videos yet on YouTube for the practice test problems, but I'll get them up there hopefully by the end of the week. Any questions on the calendar? Okay, so speaking of the calendar, and Angus had said, you know, there have been so many changes with all the snow days. So I handed out the new calendar a few weeks ago, so hopefully everybody has one of these. But I just want to point out that there were some impacts down here at the bottom of the calendar, because I kept taking off these to be announced days, but we ran out. So what happened? There was an 8th quiz on the original calendar. I've taken it off. The 8th quiz would have landed on the last day of classes, and we don't want to do that. So there are now only 7 quizzes instead of 8, although it turns out to be 8 because we had that memorize all the derivative and antiderivatives that wasn't really scheduled. Okay, so that's that. We also had on the last day of class was going to be a review day for the final. Now that's going to get compressed just a tiny bit. We'll talk a little bit about this growth and decay stuff. I'm not going to throw it on the final exam because it's the last day of the semester, but we'll talk a little bit about it, and then we'll spend most of that day reviewing. But I'm just pointing out that used to be a full period review, but because 3 snow days now, the calendar's gotten compressed a little bit. One other thing that I want to point out that's different on this calendar is the final exam. I used to have like 3 different options here. Now I'm kind of whittling it down and picking a date and trying to be flexible. So any 2.5-hour block in between 8 a.m. and 1 p.m. So that our official window is in there someplace, but I'm just trying to extend it because I have 2 sections. Any questions on how that works? Anytime. Yeah, but don't show up at 12:30. It's like right 1 is the ending of the test. Okay, so there was an extra credit thing that several people jumped on. So this was there was a website I sent you guys. So this was from Dawn. So she made this solid of revolution, very nice. And then this right here is Tacidae's. And then this one is Joe's. That's great. And I had a few other folks that sent me stuff today, and I will share it on Wednesday. I just didn't have a chance to download it. And some people actually started to describe like what the thing was that they had created, which is great. So that is that. Next thing is this announcement. Spring elections here at GCC. You guys have a student government. Spring elections are happening as of today, and they run through Wednesday. So if you want to vote, you need to vote between now and Wednesday. It all happens on Moodle. So you log into your Moodle account, and there should be some link there that it's obvious that spring elections are happening. 4 senator positions, 1 Senate president position, 1 student trustee position. Additionally, there's a referendum regarding mass purg that's going to be on the ballot. So if you don't know what mass purg is, you can read this later on, I guess, but here's what I'll tell you that you need to know about mass purg. There has been a mandatory $9 per semester fee on everybody's bill for the last bunch of semesters that goes directly to this organization. And the organization, MassPerg, claims to stand for lots of things that the Student Senate here supports, but the Student Senate doesn't feel like they have gotten the $10,000 worth of activism that you guys have paid with that everybody paying $9 a semester fee. So Student Senate wants you to get informed about this and then vote as to whether or not you keep that mandatory $9 MassPerg fee on the bill. Student Senate is in favor of getting rid of that $9 fee, but more important than their position, they want everybody to get out and vote and understand what's happening. Cassidy. That's different from what I've heard, but maybe I'm not saying you're wrong.
It's automatically placed there, and you can't leave it. You have to like buy it.
I see. I see. So you can read the thing that that the Student Senate has written up here. Anybody else want to pitch in? Okay, so anyway, that is happening, and certainly you can find more information about it up on the Moodle page. I'm expecting, is there info about this other than just a yes/no vote on MassPerg on the Moodle page? Anybody know? Yeah, so check it out. There might be there might be this in a little more detail about the Student Senate's position on this. What do you mean we've taken it and done something with it? Mm-hmm. Yeah, yeah, thank you. Right. Okay, thank you. All right, so I think that's all the announcements. If you guys could jump over to page 30, that's where we begin today. So at the bottom of page 30, we start with this example, which is one from the questions of the day. We've got this region, y equals x cubed minus x, and the x-axis, and I just want to underline that and the x-axis. That kind of reinforces some of the stuff we looked at with Dawn's example from earlier. You have to be told that one of the axes is part of the region if that's going to count as a boundary. So we've got the two curves, one curve in the x-axis, and between 0 and 1, which is the region pictured here. So we've got all this space, and we're going to rotate it about the y-axis. Now, if you're rotating it about the y-axis, can you tell me, what kind of a slice do we have to use at this point? A vertical slice or a horizontal slice? Sam, why does it have to be horizontal? Yeah, so the space is spinning around the y-axis, and at the moment, the only technique that we have for finding volumes of stuff like this is the disc and washer technique. And it turned out, and this is something that I mentioned in the YouTube video, that every slice you draw with discs and washers has to be perpendicular to the line you're spinning around. So something perpendicular to this y-axis would be something like this. So we'll draw like a little rectangle here. That right there is a typical slice. You take it, you spin it around, and you get, is it a disc or a washer in this case? We get a washer because there's a big hole in the middle. So the difficulty here is finding the length of that disc. Sorry, finding the length of that slice. Right? We need to know how much the x is out here, and we need to know how much the x is over here, because this distance is the inner radius of the washer, and this distance is the outer radius of the washer. So we need to take the equation and solve for x. And taking this equation and solving for x is really, really hard. It's not something I can do. I know there's a formula out there to solve any cubic equation. I don't have it memorized. But solving that equation for x is very, very difficult. And so we're going to want another technique. And the technique that we have, we're going to use here is a new one for us. It would be much easier for me if I could draw a vertical slice instead of a horizontal slice, because if you have a vertical slice, it's very easy to know how tall that thing is. Is it X or Y? What's a good name for how tall that slice is? Is Y, right? And how much is Y? Oh, it's X cubed minus X. It's very easy to know how tall that slice is. So somehow, I don't know, we're going to have a different kind of shape coming out of this. So I'm going to draw my circle here, and then another circle here going to the outer part of the slice. And then we got the same kind of thing up here at the top. So this guy comes here, and then this guy goes over here, and I won't draw the other part of it, but we get that kind of a shape, which is quite similar to a soup can, right? This is a cylinder with a little bit of thickness, yes? No top, no bottom, so it's not very good for holding things, but it's like a soup can other than that. And the idea is if you can find the volume of that soup can, and then look at a lot of different soup cans that sweep throughout the entire 3D region here, if we could just add up all the volumes of the soup cans, we'll have a pretty good estimate for the volume of the actual shape. The volume of the walls of the can, so not counting all that empty space inside. Yeah, so we're actually not going to use the volume of a cylinder formula because the volume of a cylinder counts all the soup that's inside. We just want the space that's actually between the walls of the can. That's what we're after. And this thing here reminds me of, anybody have, here, this is fine here. So if you have a bunch of pieces of paper and you kind of wrap them together, a single piece of paper has hardly any thickness, right? It's got some, but it's very tiny. But if you wrap a bunch of these single pieces of paper together, you can get something that's definitely three-dimensional, right? This thing is like ½ an inch thick, and I don't have that much paper here. So it's the same kind of idea. We've got these razor-thin soup cans. That's an exaggeration. That's way too thick of a soup can. But you got these razor-thin soup cans, and we're just going to stack them all next to each other, find their volumes, just the tin, and then add them all up. And so to find the volume of that can, well, one thing you could do, but we won't, is we could find the volume of the big cylinder and subtract the volume of the little cylinder. Everybody agree that that soup can thing there, if I just want the volume of the tin, I could find the volume of the outer soup can, including all the soup, and I could find the volume of the inner soup can, including all the soup. And if I subtract them, you buy that I'll just get the metal that's in between.
A slice on the bottom.
A slice on the bottom.
The outer soup can is taller.
The outer soup can, yes, the outer soup can is a tiny bit taller. So it's a really good point. The idea here is, again, that this is an exaggeration. It's way thicker than it should be. Should be something razor thin like a piece of paper. And so the extra that you might get on the top or bottom is just so negligible that it's generally okay to ignore it. But it's a great visual that you're seeing here. Okay, we're not going to do that. What we're going to do instead, again, is recognize that this soup can, the metal here, is razor thin. And so what we're really going to do is imagine maybe unwrapping the soup can and really treating it like a piece of paper. It's no longer this 3D little thin thing here. It's just a piece of paper that we've unwrapped. And what I want to do to find the amount of tin, so we'll say something like this, the volume of the tin from our soup can is very close to the surface area times the thickness of the walls. Is that something we buy? We're going to take the surface area of the soup can, and already that's a problem because there are actually two different cylinders here, right? There's the inner one and the outer one. Is the surface area for both of them the same? No, the outer one is bigger, right? It has more space to go around. So what do I even mean when I say surface area? Well, the idea here is that they're almost exactly the same. Take that piece of paper and wrap it, Sure, technically the outer one is supposed to be a little bit more surface area than the inner one, but really it's two sides of a piece of paper. It's the same, right? It's almost the same. And then we're going to multiply by the thickness of the walls. So the thickness of the walls we're going to give a name to, and it's going to be a name that we've given to the thickness of our slice, right? We've been calling it delta x now for a couple of classes. And then the surface area. So whether you call it outer or inner doesn't matter. It's this really thin thing. So how do I find the surface area of a soup can? Circumference times height. You guys buy it? The surface area of a cylinder is circumference times height. So we'll write that. Circumference times height times thickness. That sounds good. And what's the circumference? 2 pi r, that's a formula for the circumference of a circle, times the height. I just want to use a single letter. Is the height of that soup can an x or a y? That's a y. And if that's not clear, you pick a point on the curve, call it x comma y, and decide which one of them is the length that you're after. So this vertical distance here, definitely a y distance, right? So it's 2 pi r times the y, 2 pi r times the y, times, and then the thickness we were calling delta x. So that right there is a formula for the volume of that little soup can. And then just like in the last couple of classes, you'll find one of them, you'll add them all up, and then you'll let the number of things, the number of slices, go to infinity. And that's going to be our final answer at the end of this. So now let's actually go through and do the calculation for this particular function, because even though we've been looking at that picture, this formula right here is fairly general. It just is what it is. It didn't really rely on that particular picture. And we'll see this formula on the very next page. But let's go ahead and use this formula for this example. So we're going to say the volume of one can. You know what? And I'm going to stop calling it can. I'm going to call it a cylindrical shell. I think that's what your book calls it. That's what we're going to call it, to distinguish between the actual soup inside, which is not what I care about, and the shell itself, the can itself. So it is the shell that we're interested in. And it's in the shape of a cylinder with a tiny bit of thickness. So the volume of the cylindrical shell, we've got our formula over there. It's 2 times pi times the radius. So now we'll actually need to look at our picture. So the radius of this particular blue shell is this distance from here out to here, right? Is that an x or a y? That's an x, right? If you are sitting at the point x comma y, then that radius is x, just x. So let's put x. So it's 2 pi times, the radius is x, the height, the y. In this case, what's the formula for the y? X cubed minus x, right? That's what the formula is. X cubed minus x times, and then the delta x is there at the end. So we're just going to highlight some pieces. That y is there. It's the height of the shell. The radius of the shell oftentimes is just a single x. And I think that's it. Okay, there is one little detail here. What kind of a number are we going to get for the y? It's a negative number, right? Because these y's are down below. Okay, so at the end, when you get a negative volume, act surprised and then change it to positive. I mean, technically it shouldn't have been this. Technically this thing should have been the top of the region, which is a 0, minus the bottom of the region. And so that's going to take it and make it positive. It's not a big deal. Okay, so that's the volume of one cylindrical shell. If I wanted to find the volume of all of those shells, bring back our old friend sigma, and we would just grab all of the stuff that's in there. We just add them all up, yeah? 2 pi x, x cubed minus x, delta x. I'm going to do this little silly technical detail. It's not so important to me, but technically these x's should get little indices on them just so that we can say here's the first shell, here's the second shell, x1, x2, x3. And then over here we'd say, okay, let that run from I equals 1 to n, but I'm not going to bother writing that. And it's a very silly detail because when you actually let the number of shells go to infinity, those i's, and you translate to an integral, those i's just disappear. So you bring them in and then they go away right away. So the volume of the solid, that was the actual space that we were trying to find the volume of from the first place. Translate the sum into an integral. 2 pi I'll copy, although it's a constant multiple, you could bring it outside. Instead of xi, just x. Instead of xi cubed, just x cubed. Instead of delta x is dx. That always changes to a dx. And what's the only thing we have to bring in? We need the limits, right? And so this is time where you got to go back and look at the space. There are actually two answers that seem reasonable. 0 to 1 from the first picture. Oh, what seems reasonable from the second picture? Maybe -1 to 1, right? So the question is which, like one of them is right, one of them is wrong. It's the first one that's right. We only need to go from 0 to 1 because, for example, this particular x right here takes care of not just this side of the picture, but it also takes care of that side, right? It swings all the way around. So if you'd go -1 to 1, you're double counting everything. Just do the one side. The original region is all you care about. So that's what we put on the integral, 0 to 1, and that's it. And we'll end this one here. Getting to that point, getting to the integral is the ultimate goal for me. I don't so much care about the number. You can type this into your calculator or Wolfram Alpha. In this case, the integral is easy enough. You could actually do it without a calculator, but the point is setting up the integral is something that Wolfram Alpha can't do. So that's where we have to come in. And then we can let it handle the nitty-gritty calculations if we don't want to do them ourselves. Okay, so and then one last thing here, just so that we can get the right answer. I mean, it's a positive number, and the thing I have written up there is going to be a negative number, so I'll just make it positive that way. All right, so on the very next page, there is a formula that will hopefully look familiar. This 2 pi we saw, it's already pulled out of the integral. Did we see an x inside of the integral that we just did? We did. Why was there an x sitting right there? That was the radius of that shell. And then right next to the x, you saw x cubed minus x, which was the function. So oftentimes you just take this formula and plug things in. And so that hopefully looks familiar. And the only thing that I know about shells is 2 pi RH. It's the surface area of a soup can, not counting the top and bottom. Okay, so we'll take a quick look at a sketchpad thing to try to bring some of this visualization out. I'm going to go here. Imagine taking this region that's all shaded in right here and spinning it around that dotted line. So let's revolve one of these guys here. So it goes behind the board and then comes around out in front of the board. And that right there is one cylindrical shell. And you can imagine taking that entire region and spinning it around, and you get this 3D thing that we're going to find the volume of. We can find the volume of that thing by doing exactly what we did. It was just the surface area times the little bit of thickness. And that's that. And then you can revolve all of these things, and that collection, kind of Colosseum looking thing, is an approximation for the actual solid that we would get when we spin it around. The actual solid we get wouldn't have this kind of staircase thing happening, right? Because the blue curve is smooth. So it shouldn't be a staircase thing, it should be a smooth curve. But if you let the number of these little shells go to infinity, then that thing gets less and less staircasey and more smooth, right? And that's the idea of this method. We can look here, and I think it's the same thing. We will spin, there we go. So this is actually the region that we wanted to find the volume of. So that's the right answer. That's the right solid that we're interested in finding the volume of. Not staircasey at all, right? Very smooth as you walk down, but it still looks kind of like the Colosseum thing that we saw before. And we would, that's fine there if we sweep. Yeah, so those are now very thin versions of the shells that we're thinking about sweeping through. Okay, so that's the idea of cylindrical shells. Let's come back here and try this one, number 4. Before we do number 4, there's one more announcement. Privacy Week is happening this week here at GCC. This afternoon at noon in the library, there is an expert, Cade Crockford, an expert on data mining from the Massachusetts ACLU. Also, there's food. So if you want to go and learn about privacy and data mining and what you should know about about your activities, behaviors on the web, you might check it out, or some of the other events this week. Right, so that's the library today at noon. Okay, so we've got this region bounded by y equals x squared. So we'll start by drawing a good picture. What's another name for y equals 0? It's the x-axis. So we got the x-axis. And then x equals 2 is what kind of a line? It is straight, it is vertical. So that right there is x equals 2. So that's the region that we're spinning. I'll also say that oftentimes it takes a couple of iterations before you get a nice picture in front of you. Sometimes what happens is, you start with the axes and you draw y equals x squared, and you draw, let's see, in green, x equals 2. You say, okay, there's x equals 2. And the region that you found it, it's this space right in here. It's that region, but this is not a good representation of that region. So you draw it again. Once you find the thing, you draw it again nice and big so that you can actually visualize what's happening. So we're going to take that region and spin it around the x-axis. And it says we want to use the method of shells, cylindrical shells. So we'll take this thing, spin it around. I'll go ahead and draw another copy of this guy down here. So you imagine that solid going around. It kind of looks like the end of a trumpet, right? Except it's completely filled in. This is a solid thing that we're trying to find the volume of. So if we wanted to find the volume using this idea of shells, we need to draw the right kind of slice. And the right kind of slice is either parallel to the axis you're spinning around or perpendicular to the axis you're spinning around. And which choice you make dictates whether you're doing a discs washers thing or a shells thing. And so I think I mentioned this in one of the videos to remind me, but I think I said something about if you're doing discs and washers, the slice is always perpendicular to the axis. And if you're doing shells, the slice is always parallel to the axis. Does that sound familiar to anybody? I think that was in the last class's notes. So if you're doing shells, slice is parallel. And that kind of makes sense. And I'll just draw one quick slice here that's not parallel. If I draw something perpendicular to the axis I'm spinning around, and I take that thing and spin it around here, what kind of a shape do I get? I get a disc, right? It's just a big old circle filled in the middle. It's not a soup can at all. So what we want to do is draw something parallel to the axis. So we're going to go ahead and draw this thing parallel to the axis that we're spinning around. And I'm going to label this picture. And I think that labeling the picture in the right way makes it really easy to set up the integral when we get there. I'm going to put a label on this point. I'm going to put a label on this point. So let's go ahead and put a label on this point here at the far right. How much is the x at that point? It is 2. It is always 2 if you are on that vertical line, right? You just imagine taking that slice and sweeping it up and down. The far right-hand point is always 2 comma something. What's a good letter to use for the something? It's y. Just some generic y value. And now that we've made that choice, we'll come over and label the other point. Is the x constant at this left-hand point as you slide the thing up and down? It's not. The x moves, right? If you're on a slice up here, the x is something close to 2. If you're on a slice way down here, the x is something close to 0, right? So the x changes depending on where you are. So we'll call it x. That's a good name for the second letter. We can call it x squared. I'm going to call it y first, then we'll translate it. But have I made a mistake here calling this y when I already called this y? Is it the same y, or do I need to have like a y1 and a y2? It's the same y, because that black slice, the horizontal slice there, it's whatever y is, it's the same at the left and at the right. So that is a good choice to use the same letter. And then we're going to take Garrett's suggestion here. Let's do one more thing, and then we'll do Garrett's suggestion. It feels like we want to know, or we want a name for the thickness of the slice. Delta something, delta what is a good name for the thickness of that slice? Delta y, right? It's a little tiny change in y that's happening on the thickness of the slice. And given that it's a delta y, what is that going to become in an integral? dy, which means all the variables in that integral have to eventually become y's. So then we really like Garrett's idea here of changing. So we're going to translate this point right here. Which letter do I like, x or y? I like it to be a y. I don't like the x. So what I need to know is how much is x in terms of y? Well, the defining characteristic for that point right there is that it's on the blue curve. What's the equation of the blue curve? Is y equals x squared. So you can take this thing and solve for x. I don't want x's, I want y. So how much is x? X is the square root of y, yeah? So that's what we'll put over here. Okay, so we've done that work. Now we're going to draw the mirror image of our slice. So I'm not going to draw the thickness part. I'll just draw one of them. So we've got kind of a really thin cylinder there. And again, the only thing that I know about cylindrical shells is what Joe had told us before. The volume of a shell is very close to the circumference times the height of the shell. 2 pi times the radius times the height. That's all that I know. So the radius of that shell, which is this distance from here to here, although it doesn't quite look the same as the radius on the other side, but I can ignore that. What's a good name for that distance? Is that an x or a y? That's a y, isn't it? So the radius is y. the height of that shell. That's it. It's 2 minus root y. The height is this distance from here to here. That distance is a change in x. So you just got to figure out how much x is when it's big and how much x is when it's small and subtract them. 2 minus root y is the height. And I'll put down here, this is the big value of x, and this is the small x. I'm missing something here. There should have been a times thickness at the end of this guy. And again, what was the symbol we used for the thickness of that shell? It was delta y. That's it. So let's go ahead and skip over the sigma part. We'll just jump right to the integral. So I've got 2 pi, I've got y, 2 minus root y. That's all copied from over there. Delta y becomes dy. And the last little bit of work, and there is a little bit of work, is to figure out what those limits are. And really imagine that slice sweeping through, just like in that sketchpad thing that we saw before. That slice is sweeping up and down. So how much is the y at the bottom slice? Is 0. And how much is y at the top slice? Well, we haven't figured it out yet, but it's whatever y is at the point up there. Two folks say 4, is that right? Just plug x equals 2 into that curve. So we're going from 0 at the bottom up until y equals 4 at the top. Yeah. So the extra y, do you mean this one, Dawn? Or okay, yeah. So that one is actually not the h, that one is the r. So if we're looking at this this soup can right here, Joe tells us that the surface area of the soup can is 2 pi rh. So we need to know what the radius is. So the radius is this distance right in here. It's also this distance here. I didn't draw it quite symmetric. So the radius is from here to here, which is the same as from here to here. So would you say that that distance right there, is that an x distance or is that a y distance? That's a y distance. So whatever the y is right there, that's what the radius is. So what is the y? Well, we just gave it a generic name. We called it y. And so that's the y that you see there. Yeah, the h is the other part. The h is the 2 minus root y. It's the height of the cylinder. And the height of the cylinder is however much x is out here minus however much x is here. This distance right here is just a change in x. So we took the x that was big and subtracted the x that was small.
So Stacey said that when we're visualizing
Mm-hmm.
that, is it all the time? I mean, I usually do, but that the y is 90 degrees.
So yeah, actually.
Yeah.
Yeah, so this space, I haven't drawn the space that we get when you take this region here and revolve it around, that kind of filled in horn thing, it goes into a third dimension, right? All we can draw up here on the board is the x and the y, but there is a z, and that's basically what Calc 3 is about, is that going past just the two-dimensional stuff here. So the common letter for the other axis, the one that's coming out of the board, is z, x, y, and z. So yeah, Maggie, the y-axis is 90 degrees from the z. Also, the x-axis is 90 degrees from the z.
Right.
Yeah, so they're all three mutually perpendicular to each other. Yeah, so it comes out and then goes back behind the board. Other questions on that? Okay, so we're going to skip this next part. It's just a formula, and I'll let you practice. Well, you will practice it for homework, but it turns out that if you want to find the length of a curve, you do this integral right here. If you want to find the length of a curve, you do that integral. we're not going to go through the derivation. We'll just do one quick example here. But the derivation's in your book. And again, if you look through it or if you see me after class, hopefully we'll see why an integral is appropriate for arc length. But let's go ahead and take a look at one quick example right here. Number 6. I want to find the arc length of y equals cosine x between 0 and 2 pi. So if we were actually walking along that curve, we want to know how far we'd have to walk. Or if you had a piece of string, you could match it up with the curve and then straighten it out against a ruler, find out how long it is. So just a quick estimate. If this were a straight line from there to there, how far would it be? 2 pi. Yes? If it were a straight walk, it would be a distance of 2 pi. Is our walk more or less than 2 pi? More, because we're going way down and way out of our way and then coming up. So it's more than 2 pi. If you wanted to get a better estimate, maybe you'd say, okay, forget the green line at the top, but let's just approximate the curve with 2 of those lines. We could find those 2 lengths, right? I mean, you guys have a distance formula. In fact, write it here, distance, square root of something squared plus something squared, right? That's the distance formula from back in algebra class, which does look an awful lot like the thing we're doing here. We have an integral, but we also have a square root. We have something squared for that formula we're about to use. So anyway, the idea of arc length is that you'll just draw lots of little line segments here. And the more of these little line segments you draw, the better the estimate, right? Like this estimate is better than the straight line across. So let's just use the formula. So here it is again, maybe L for arc length. So integral a to b square root 1 plus f prime of x squared. So with the formula, it's pretty easy. It's just a plug and chug. Integral from where to where? 0 to 2 pi, it's given. Square root of 1 plus something squared. The something that goes in there is the derivative of the function. What's the derivative of cosine? Negative sine. And we'll just go ahead and rewrite that as a positive sine squared. So that's what we're after. Any questions on plugging into the formula?
Does it end up being 1 in the formula?
Yes. That's why there's a 1 there. Okay. The little lines that we're drawing, I'll try to draw in red maybe. So the same idea as drawing 2 green lines, but really instead we're gonna draw a tiny line there, tiny line there. We're just gonna keep drawing these little secant lines. And so maybe this is about 20 of those lines. And finding the lengths of 20 line segments is easy, right? You just keep using that blue distance formula from algebra class. But the idea is we don't want to use 20 line segments to approximate the cosine curve. How many do we want to use? Infinitely many. And using infinitely many of those little things, okay, maybe now the integral isn't so surprising as the final answer. Okay, finding the integral of that, is that something we can do by hand? If you can, you should show me, because I don't know how. Feels like maybe there's some identity we can pull, right? We got 1 plus sine squared. I don't know. But if you find a way, let me know. The arc length formula rarely gives you something you can actually do by hand. So somebody type this into a calculator for us so we can get a sense. And while we're waiting, just a reminder that hopefully there are 3 homework assignments from folks in the green folder, right? 16, 17, 18, the 2 that I wasn't here to collect, and then the 1 that's due today. Anybody have a number here? And once we have our number, we'll spend the last 25 minutes or so doing these examples here. And let me just point out, there's one kind of funny thing. So there are 3 examples with answers. Where's the 1, 2, 3? Oh, that's 1. What is it? Both of those numbers sound too small to me. 7.64. Okay, so there you go. If you walk one part of a cosine curve, the mistakes, it's very easy to make a mistake typing that thing into the calculator. So there you go. So if you walk one period, one cycle of the cosine curve, you are walking 7.64 units. That's how far it is. Okay, so there are...
I'm having trouble visualizing what that would cause. Like I get what a integral tells us. What does that tell you?
What does it tell me?
Like if that cosine function was like velocity or linear race, what does that tell you?
That's a good question. Let me think about that. Okay, so let's get folks started on this group thing. So there are several different parts down here and an answer key, which I'm a little bit concerned about because it doesn't seem to match the number of questions here. So that's kind of funny. But you guys will let me know. So I see A, B, and C in this group activity. Somehow a 1 and a 2 in the answer key. So again, figure out what I did wrong there. But I want to point out in the homework that on the very next page, there's a photocopy of a book or a couple of pages of a book, which is going to be part of your homework. So on the next page, it says do 3, 5, and 7 from the Stewart handout. That's the photo or the scanned thing that's on the previous page. Okay. And there, I also scanned in the answers down at the bottom, I think. Yeah, right there. Okay, so let's see how far we can get on the previous page.